Perfect timing, isn't it? Music. We're witnessing a truly extraordinary and uncommon event right now. The object known as 3I/Atlas is gliding past Mars. Starting October 4th, 2025, it's moving farther from its nearest pass by the red planet, though it remains near enough to be significant. Only the day before, on October 3rd, it reached its minimal distance to Mars as viewed from our planet. Capturing images at this stage proves nearly impossible. Solar brightness overwhelms the area, with the object tucked away in its glow. This leaves the probe circling and exploring Mars as our sole reliable viewpoint for observing 3I/Atlas currently. Strangely enough, numerous NASA sites and streams have fallen quiet due to a federal budget halt, hitting right when we crave live information. Cutting off essential public info amid a cosmic close encounter seems suspiciously timely, particularly as scientists globally scramble to track what could be the oddest visitor in our solar system yet. Speculation is already rampant. Certain experts float the idea of an unusually vigorous comet, nothing like prior ones. More adventurous notions include an extraterrestrial scout, advanced tech fragment, or even spacecraft from another world. Plausibility aside, this info blackout's coincidence sparks suspicion. Luckily, there's a potential breakthrough. The Perseverance rover snapped a line across a series of multi-minute shots on October 2nd. This line doesn't align with the typical sky movement on Mars. Rather than running straight up or matching the star paths from planetary spin, its angle stays oblique and steady through the frames. It's genuine. No error involved. It's zipping along swiftly. A strong case exists that this captures 3I/Atlas in action. Shout out to Drew for spotting this line in a Twitter update, which prompted deeper analysis. The object's dimensions stay unknown, but initial guesses hover at a minimum of 5 kilometers across, maybe larger. It shows no massive traditional dust tail like classic comets. Rather, it appears shrouded in a broad, fuzzy envelope of charged gas and particles. Its velocity is stunning, around 60 kilometers per second, ramping up to nearly 68 kilometers per second as it heads to perihelion late this month. Back on September 25th, a solar flare blast hit 3I/Atlas, possibly charging its atmosphere. Subsequent photos from September 27th and October 2nd reveal no dramatic changes, no abrupt tail split or breakup, just subtle signs of the sheath slowly widening. That's what made NASA's reporting so vital to the community. But we're not out of options. ESA's Mars Express and ExoMars Trace Gas Orbiter were positioned for a close-up look at 3I/Atlas, grabbing photos and gas/dust tail spectra. The JUICE probe ahead will cross paths with it en route to perihelion. Still, solar interference will lag data transmission. Combined, these tools might paint a clearer picture of 3I/Atlas. Attention turns to ESA now, our prime shot at fresh visuals of the object. Music. Just how large is 3I/Atlas? Determining a comet's true scale is tricky business. The issue stems from separating the solid core from the misty halo encircling it. As a comet nears the sun, its icy components sublimate into vapor, hauling dust particles outward to create the signature blur or coma. This effect can swell the comet's visible size and glow well beyond the rocky center. Recently, a Harvard group under Richard Kluta, Avi Loeb, and Peter Verez examined data on 3I/Atlas from May 15th to September 23rd, pulled from 227 observatories through the Minor Planet Center. They contrasted the real path with a purely gravitational one. Their discovery, a small yet detectable nudge, under 15 m per day squared. Typically, outgassing comets experience a gentle thrust from venting gas streams. For 3I/Atlas, though, the detected non-gravitational pull is oddly subdued compared to its evident activity. This implies a hefty nucleus that barely budges under those outflows. Based on that, the team pegs the core at more than 33 billion tons, with about 5 kilometers diameter, excluding the coma, and it's 3 to 5 orders heavier than previous interstellar wanderers. Loeb points out that, considering interstellar object counts and metal densities out there, we'd expect many smaller ones by now before hitting such a behemoth. But that's not our experience. This positions 3I/Atlas as a major anomaly. Loeb goes further, pondering a tech-based origin, pointing to the surprising bulk, path precision, and alleged nickel signals sans iron as intriguing clues. NASA experts, meanwhile, advise restraint. The prevailing view holds that it's probably a natural formation. From the photos, we've observed that this thing is dynamic, suggesting a hazy envelope surrounds its core, a clear sign it's actually a comet. On the other hand, certain researchers aren't just wondering what 3I/Atlas represents. They're pondering its potential role. Astrophysicist Suzanne Fner's concept is straightforward yet compelling. 3I/Atlas could act as a seed for planet formation. But how might a rogue rock from a distant star system trigger the creation of a whole world? Let's explore the process. Picture a fledgling solar system, with a fresh star at the heart of a vast, dusty disk. In this setup, minuscule rock particles whirl around like mist, gradually merging into small stones. Over time, these expand into larger rocks and eventually into planetesimals, the basic building blocks of planets. Eventually, they bulk up sufficiently to attract additional debris. It seems simple enough, yet as we'll discover, this model faces a major hurdle. Protoplanetary disks endure only a handful of million years before the gas dissipates. That brief period appears insufficient to account for the development of enormous worlds like Jupiter and Saturn. Consider an alternative picture now. An extraterrestrial visitor tumbles into the disk, a chunk already sizable enough to function as an instant nucleus. Rather than building from scratch with fine particles, the disk gains a sturdy foundation that can swiftly draw in nearby gases and solids. Through this mechanism, such an outsider might accelerate the emergence of a new planet. Fner's computer models back this hypothesis. She determined that larger stars excel at snagging interstellar intruders compared to their smaller counterparts. And indeed, giant gas planets tend to orbit heftier stars more frequently. The alignment of prediction and evidence is remarkable. Should this hold water, then wanderers like Oumuamua, Borisov, and Atlas aren't mere passers-by. They could be the catalysts that kickstart planetary architectures. A few may have nucleated massive gas worlds in remote setups. Some might have influenced our own system's formative days. It's an audacious theory, remaining unverified for now. Similar to Oumuamua, these interstellar bodies prove challenging to examine closely. They pop up abruptly, zip through space, and fade into obscurity. Yet in this instance, we've spotted it early on, putting us one step ahead. Our advancing tools could at last reveal its authentic character, instead of relying on post-facto speculation once it's departed.